This video is designed to help you simplify expressions that have roots or radicals in them. Here's an example of a fairly simple multiplication problem, but we're going to take advantage of the following principle, and that is that the square root of a times the square root of b equals the square root of a times b. Now, what that really means is that if we have a product of two roots, such as the square root of a and the square root of b, we can combine that into one root, which is the square root of a times b. But conversely, we could start with the square root of a times b, and if it helps us to simplify, split that up into the square root of a times the square root of b. For the sake of expediency, we're going to assume that all any variables that we wind up simplifying in this video are all positive, so that we're not having to worry about negative square roots, the square roots of negative numbers and that sort of thing. But at any rate, what we're going to do is take advantage of the fact that this is a bunch of multiplication, and we're going to use commutative property to rewrite it as 3 times 4 times square root of 2 times square root of 14. The 3 times 4 is clearly going to be 12, and the square root of 2 times square root of 14 we're going to rewrite as square root of 2 times 14. Now, the square root of 2 times 14, what we're really interested in doing when we simplify a root is finding pairs of prime factors. So if we prime factorize this, what it is 2 times 2 times 7. We could multiply it out to 28 and then prime factor it, but of course that would be doing more work than we need to do. So we'll just simply prime factor the 14 and combine it with the 2's. Now, any pair of factors can be rewritten as its own, under its own root sign, and it's the square root of 2 times the square root of 7. So now we're going the other way with this idea that we have over here. So really this idea is simply that we can, any multiplication, we can either split into separate roots or not. After a while you can just visualize it and you don't really need to do it formally. But in this case, what we know is that the square root of 2 times 2 is the square root of 2 squared. So we're unsquaring 2 squared, which means that answer is 2. What this effectively means is we can pull a 2 outside the square root sign, since we have a pair of 2's inside the square root sign. We can't pull the 7 out because there's only one factor of 7 in there. So our final answer is going to be 24 root 7. And that would be the finish to this problem right there. So let's go on and take a look at a few other problems. So here's a very similar problem, and once again this is a number of things multiplied by each other. 3 square root of 5, square root of negative, the opposite of the square root of 10, and the square root of 27. So if we move this around to 3 square root of 5, and we're going to put the minus sign out in front because basically it's 4 things times each other, one of which is negative, so the answer is going to be negative. And so we're going to have square root of 5, square root of 10, and square root of 27, which we can put all under one radical roof. And so we're going to get the opposite of the square root of 3, and now I'm going to prime factor everything. We're going to have 5 times 2 times 5 times 3 times 3 times 3. So formally what we can do is we have a pair of 5's that we can pull out, and that's going to give us negative 3 times 5 on the outside. And we also have a pair of 3's that we can pull out, so that's going to give us times 3 on the outside. And we will have left on the inside a 2 and a 3 without partners that we can simplify to. And so 3 times 3 times 5 is 45. So this is negative 45 root 6. That would be the simplest version of this problem. Let's take a look at some others. Now we're going to start dealing with roots on the denominator, and also using conjugates to help us either rationalize roots or do some multiplication. We'll take a look here. So here's an example of a multiplication that we need to do, and we'll not be simplifying anything, or we will be trying to simplify this result, so we should get rid of the parentheses. What that means is we'll be distributing this to this term and this to this term. So that's going to give us 2 root 7 times root 7 minus 2 times 4 times root 7. And of course this is going to be fairly simple. That's going to give us 2 times 7, because root 7 times root 7 is 7. Square root of 7 squared is 7. Minus 8 root 7. And we are done. I'm sorry, I should simplify the 2 times 7, of course. So that's going to give us 14 minus 8 root 7. And there isn't anything else we can fully simplify there. So there's a fairly straightforward example of multiplying out the distributive property with roots involved. Let's take a look at some more. Here's a very similar problem, but we're going to see that there's a little more simplifying going on. So once again, we'll do this distributing. And what we're going to get is 5 root 36. Oh, that sounds nice. And we're going to get square root of 18 times 18, which of course is also nice. Root 18 times root 18 is then just going to be 18, which we'll be subtracting, and 5 root 36, of course, is 5 times 6, so that's going to give us 5 times 6, and so when we simplify all this, we're going to get 30 minus 18, and we will get 12, so there's a pretty quick one. We'll take a look at some more. Here are 2 examples of multiplying out binomials that have roots in them. So the first one is going to be a perfect square, so let's write out exactly what we're going to look at. And it's going to be root 6 minus root 3 times root 6 minus root 3. And of course what we need to do is FOIL this out. So the first is going to give us root 6 times root 6. The outers is going to give us root 6 times root 3, and that will be negative. So that'll be root 18. And then the inners is going to give us root 6 times root 3, which is also root 18. So we'll write minus root 18 again. And the last is going to give us root 3 times root 3, and that'll be positive. Root 3 times root 3. Okay, and what we're going to see from this, of course, is that the root 6's multiplied by each other gives us 6. Now, what we can do is we can collect root 18's just like we can collect n's or x's. So this is going to give us minus 2 root 18. And of course, the lasts are going to be root 3 times root 3, which is just plus 3. Remember, a negative times a negative is a positive. So now we can collect our whole numbers, and so that's going to give us 6 and 3 is 9 minus 2 root 18. And theoretically we're done, except that the root 18 can be simplified, and that's going to give us 9 minus 2 times, and of course root 18, if we factor that, is 2 times 3 times 3, so there's a pair of 3's we can bring out, so that's going to give us 3, and there will be a root 2 left in there, which means we have 9 minus 6 root 2. So there's an example of multiplying out a perfect square involving roots. Now we're going to take a look at a special case of multiplying out binomials that is actually going to give us the difference of 2 squares, which we'll take advantage of in a couple future slides, looking at some other problems. These are called conjugates of each other, or often called conjugates of each other, but it's a number plus a number times the original number minus the second number. And of course this is the pattern for difference of 2 squares. So if we look at this, what we're going to get is 7 times 7. I'll explicitly multiply out the FOIL, so it's going to be giving us, If we do the outers, that's going to be 7 root 2. Sorry, that'll be minus since we're doing the outers. So that'll be 7 root 2. And the inners will be plus 7 root 2. And then the last is going to be minus root 2 times root 2, or root 2 squared. And of course that's going to give us 49 right here. And it's going to give us minus 7 root 2 plus 7 root 2. So those cancel. These guys cancel. And we're going to get minus root 2 times root 2. And that gives us 2. So the square root of 2 times the square root of 2 is just 2. So this answer would be 47. So what you'll notice here is that when we multiply conjugates of each other, that is, take advantage of the difference of two squares patterns. If there are roots involved, we can eliminate those roots because the outers and inners cancel each other. So let's see how we can take a look at that in a couple of slides by rationalizing the denominator. So on this slide, what we're looking at is two fractions, and to simplify a fraction involving roots, you're not allowed to leave roots on the denominator. So in this first problem, all we're looking at is a fraction that we need, that we could cancel, except that things don't cancel. So it's pretty easy to clear the square root of 3 by multiplying both top and bottom by root 3. If we do that, we will of course eliminate the roots on the bottom, because what we're going to get on the top is 6 root 15 over root 3 times root 3, which of course is just 3. Now, of course, you should always look to see if you can simplify it further, which in this case we can. So what we're going to get is 2 root 15 when we simplify this sort of messy looking original fraction. Now, the second fraction on the right looks even messier, but what we're going to do is take advantage of that complex, of that conjugate multiplication that we saw on the problem before. And what we're going to do is we're going to rationalize the denominator by multiplying by root 5 minus root 2. That's going to give us the difference of two squares on the bottom, and therefore we have to multiply the top by root 5 minus root 2, and that's going to give us an equivalent fraction. And of course the numerator is now simply 4 root 5 minus 4 root 2 if we've distributed properly. And on the denominator, what we're going to get is root 5 squared, which is 5, minus root 2 squared, which is 2. So that's going to give us 4 root 5 minus 4 root 2 over 3. And that's going to give us our final answer, since the 3 won't cancel with the 4's. If, for example, this had been 6 root 5 minus 6 root 2, we could have canceled the 3 with the 6's and reduced that down, similar to what we did on the previous problem. Okay, let's take a look at one more problem just for practice. Here's an example of one more problem to simplify. Let's again take advantage of multiplying by the conjugate. You should try this for yourself if you're unclear right now, but 3 plus root 8, and of course that's going to rationalize the denominators for us. So when we multiply this out, we're going to get root 5 times 3 plus root 8, and we'll be wanting to do some simplifying there, but 3 minus root 8 times 3 plus root 8 is going to be 3 squared. So let me write this as the difference of two squares right now. Square root of 8 squared, just as a reminder. And of course the top then is going to be 3 root 5 plus root 40, which we'll clean up in a little bit. And on the denominator we're going to get 9 minus the square root of 8 squared, which is just 8, which gives us a denominator of 1, which is really nice. Since that means the denominator goes away, this right here is just equal to 1. And so what we're going to get is 3 root 5 over 1, which is just 3 root 5, plus root 40. Now with root 40, we're going to pull out any pairs of factors, and so what we have is 2 that we can pull out because there's 4 in 40. That leaves us with root 10, and so what we're going to have is 3 root 5 plus 2 root 10 is going to be our answer. Hope that's helped.